Okay, in this video we're going to talk about the definition of a vector space. So, vector spaces. And they generalize Rn. Rn is an example of a vector space, but a vector space is an abstract concept. Let's look at an example just to motivate the definition before we jump straight to the definition. So for instance, let's say that we had some linear system, say, let's say you had x1 plus 2x2 plus 5x4 equals 0, and negative x1 minus 2x2 plus x3 minus 6x4 plus x5 equals 0, and negative 2x1 minus 4x2 minus 10x4 plus x5 equals 0. And you have this linear system of three equations and five unknowns. Now it turns out that the solution to this system is the set S, which is the span of the vectors negative 2, 1, 0, 0, 0, and negative 5, 0, 1, 1, 0. And this is a subset of R5, right? Now this is not just any subset of R5 though. It's the span of a list of vectors. So note that S is closed under addition, and it's also closed under scalar multiplication, right? Any span of a set of vectors, it satisfies these properties. And so it has that. And it also has the property that S contains the zero vector. Well, that's actually part of the condition of being closed under addition and scalar multiplication. But the point I'm trying to make is that this set is not just any set. Somehow, if you add two elements in S, you stay in S. And whenever you scale a vector in S, you remain in S. Now this isn't true whenever you just have an arbitrary set, right? If you just have a random set and you take a vector in it and then double that vector may very well not be in the set. Okay, let's look at another example. And we'll see that in our definition of a vector space, S is an example of a vector space. Okay, let's look at a very different example. Let's let A and B be real numbers. Numbers with A less than B. And we define C of AB, C brackets AB, to be the set of continuous functions. So these are continuous real-valued functions defined on the interval AB. So all right, fine. You can have continuous functions on this interval. Now the elements of the set are functions, right? By definition. And functions don't look like vectors, but the functions in the set do satisfy some features that are in common with vectors. So for instance, if F and G are elements of the set, you can define the sum, F plus G. We often do this kind of automatically, but we should single out that this is really a definition. We can define f plus g to be the function defined by, so this is a function, and what it does when you plug in x is you take f of x plus, and then you add g of x, right? So this is a definition. Now it's a calculus fact that when you take a continuous function f and a continuous function g and add them, what can you say about the result? It is itself continuous. F plus g, so by a calculus fact, I'll just say by calculus, f plus g is also a continuous function on the interval ab. And we can also do the same thing by scaling. If f is in CAB and you take a scalar c, then we can define, right, c times f to be the function. Okay, so to define a function, I have to say what it does to an arbitrary input. So this is for x in this interval AB. I have to define what it does to an input, and what it does is it just takes f of x and multiplies it by c, right? So this is also a definition. And notice that if f is in CAB and c is a real number, then CF is also a continuous function on the interval from A to B. So even though the set C of AB doesn't look like an element of Rn, right? It actually has properties of the span S in the previous example. Now S is not a Rn, it's not an R anything, right? S is a subset of R5, but it's not R2. We don't call it R2 because R2 is a set of two tuples, right? The elements of R2 have 2 components. The elements of S have 5 components, but it behaves a lot like R2. It's the span of 2 linearly independent vectors. You can add 2 vectors and in S and get an element of S, and it's closed under scalar multiplication. So it behaves a lot like R2, and this C of AB, it's a different example. In fact, this is in some sense infinite dimensional. It's not somehow 2-dimensional or 3-dimensional or anything. It's not finite dimensional, but it still has properties that that the S in the previous example does. And these properties are similar to the properties of Rn. And so all of this is to say that we want some notion that, some term that describes all of these at the same time. So with that in mind, we make the following abstract definition. And so we're ready to make this definition. So here F will denote a field. And the definition is a vector space over F. A vector space over F consists of, now this is a very long definition, but it'll make sense. So it consists of a set V together with operations plus called vector addition. So in other words, it's not just a set, there needs to be a way to combine elements of V by addition, some operation called addition. So it has this operation called addition and this operation dot called scalar multiplication. And an element called 0 in V such that all of the following holds. All of the following properties hold. So the first one is that the sum of two vectors is a vector. Well, that's the slogan. More precisely, what this means is that for each v and w in v, v plus w is itself an element of v. Okay? So, you can't add two vectors and then get something that's not a vector. The sum of two vectors is a vector. The next one is that for each C and F and V, CV is an element of V. So what this says is that a scalar multiple, any scalar multiple of a vector is also a vector. Okay, that's completely natural. The third one is that vector addition is commutative. So vector addition is commutative. More precisely, for each v and w in v, v plus w equals w plus v. All right. The fourth one is that vector addition is associative, which means that for each u, v, and w in v, if you do u plus v and then add w, that is equal to what you get by taking u and then v plus w and then adding them. Okay, this is completely familiar from Rn and your experience with real numbers. And it's also true for functions, right? If you have function addition, it's associative. So the fifth property is that for each v in v, v plus 0 is 0 plus v, and it's also equal to v. Okay, so this element 0, which is part of the definition of a vector space, this 0 element has to have the property that when you add any vector to it, you get, in either order, you get v. So that's the fifth property. Then the sixth property is for every v in v, there is an element w in v such that v plus w is 0. So what this is saying is that there exists an additive inverse, existence of additive inverses. So an additive inverse of an element is something that you can add to it to get 0. And this is what property 6 is saying. There is an element w that you can add to v such that v plus w is 0. And in this case, we often, actually, maybe I'll say that later. So that's property 6. Then 7 is the property that So here we're talking about vector spaces over a field, and every field has this element 1 in it, right? So property 7 involves this element 1, and it's for each v in v, 1 times v is just v. right? So this one is the one, it's the unity or whatever, the multiplicative unity, whatever the term is, in the field F. Okay? Then the eighth property is, we're almost done, there's 10 of them. The eighth property is that for each A and B and F, and for each V and V, if you do BV and then multiply that by A, that's the same as taking AB and then scaling V by AB. So AB is an element of F, right? Okay, that's property 8, and then property 9 and property 10 are about the distributive property. And I'm breaking it up into two pieces. So for each A and F and V and W in V, if I add V plus W and then scale it by A, it's equal to what I get by scaling V by A and scaling W by A and adding them. So that's the first distributive property. And then the second one is that for each A and B and F and V and V, if I take A plus B and then scale V by that, that's the same as AV plus BV. So these two, 9 and 10, these are the distributive properties. Period. That's the end of the definition. And it's a very long definition. It takes up the whole page. And it took up more than a page. But the idea is pretty simple. It's just the idea is that it's a generalization of the kinds of properties that we want vectors to have. So these general vectors, right? And so, and the vector is an element of a vector space. So we say that a vector, we define a vector to be an element of a vector space. Right, so the set V consists of elements. Okay, those elements are called vectors. Right. So a vector space, to summarize, is just any collection of things. We're not actually saying specifically what a vector space is, right? We're just saying what are the properties of a set that we want to call it a vector space, and it's these 10 properties. If you have any set whatsoever, it doesn't matter what the set is, as long as that there are these operations, plus and times, the addition of vectors and the scalar multiplication, such that these 10 properties hold, then it's called a vector space. That's the definition of a vector space. Right, so previously you might be used to thinking of a vector as an element of Rn, but now it's just an element of any vector space. So the bottom line is a vector space over a field F consists of a bunch of things called vectors that you can add to each other and multiply by elements in F, and those operations behave basically as you expect. And when F is R, we call a vector space over R a real vector space. And when f is C, we also call a vector space over C a complex vector space. So if you hear someone say a real vector space, they just mean a vector space where the scalars are real numbers, and similarly for complex vector spaces. Okay, so let's go back to the definition and make some remarks on the notation. So as you might expect, oftentimes when you have a scalar multiplied by a vector, we don't write the dot, right? So C dot V, we often just write as CV. And the other remark is when we're talking about the existence of additive inverses, here, V plus W is the zero vector, we often write W as negative V. Okay. So as you're reading this, I might no longer write arrows over the V and W, elements of V, so you just have to keep in mind, right, whether these elements are elements of the field or are vectors. So let's just show quickly that we have some examples of familiar vector spaces. So proposition is if f is the field and n is a natural number, then if you define Fn to be all n tuples, where the AIs are in F, then this is a vector space over F where we define plus, so we define A1 through AN plus B1 through Bn to be, by definition, A1 plus B1 to AN plus Bn, and we define scalar multiplication in the usual way, that this is a vector space. Well, we have to show that there is a zero vector, vector 0 with the property that when you add 0 to V, you just get V. So we define the 0 vector to just be 0. Then we claim that 0 is, then this element satisfies, where is it, property 5, because if you have a vector V, let's not do the arrow, if you have a vector V, which is say A1 for AN, then 0 plus V, I'm so used to drawing the arrow above it, V is equal to, well, it's 0 plus A1 through AN, and this is by definition A1 through AN, this is V, and V plus 0 is this, and this is equal to A1 through AN by the definition of this addition. Right, we're defining the addition to be like this. And so this is equal to V. And so this shows that when you define 0 to be the vector consisting of all, 0, then 0 plus V and V plus 0 are in fact equal to V. And the other properties are pretty much trivial, okay, but I think we should check the distributive property. So let's also check this. Let's do one more. Let's check property 9. So this says, property 9 says that if you take a scalar c and then two vectors a1 through an and b1 through bn, we want to show that it's c times the first vector plus c times the second vector. That's what property 9 says. Let's check that this is in fact true. So this is equal to, by definition, c times, so we add these two vectors first, right? Now we use the definition of addition, and we get a1 plus b1 to an plus bn. Now we use the definition, so this is by definition of vector addition. Now we use the definition of scalar multiplication. Did I define scalar multiplication? Yes, I defined scalar multiplication. I defined this symbol to mean this. So by definition, this symbol is equal to what I get when you take c and then multiply it by a1 plus b1, dot 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 c times an plus bn. So this is by definition of scalar multiplication. How do we get here? This is by definition of vector addition. And now this is equal to CA1 plus CB1, CAN plus CBN. How do we justify that these two are the same? Remember the AIs and BIs. What are the AIs and BIs in this definition? The AIs and BIs are by definition elements of a field, F, right? And so, by the properties of the field, the distributive axiom of a field, C times AI plus BI is just C times AI plus C times BI. So this is by the distributive property of a field. This is one of the field axioms. So that's how we get from there to there. Now this, we want to split up as CA1, CA2 to CAN plus CB1 to CBN. Now is it true that this is equal to this? Yes, how come? We're using the definition of vector addition. By definition of vector addition, right? If you have these two vectors, this vector and this vector, how do we define the symbol plus? We add the components together, and when you add the components together, you get this. Okay, now this is equal to C A1 through AN plus C B1 through Bn. Why is that true? This is by definition of scalar multiplication, right? We defined this symbol to be this, and we defined this to be this. So therefore, this whole thing is equal to this. And now, are we done? Yes, right? because we wanted to show property 9 says that this thing is equal to this thing. And we just showed that they're equal because they're all equal to, all these vectors. And so that's the proof. So notice that all we used was the axioms of a field and the properties of the definition, the way we defined the addition and the scalar multiplication. We showed that property 9 of the vector space properties is actually satisfied. And so, we checked one of the properties that we need to check in order to show that something is a vector space. And we showed property 5 also, right? Okay, well that leaves 8 more properties to prove, but they're all similarly kind of easy to check. Where are they? Here. They all essentially follow from using the definitions, but it is a good idea to go through each of them carefully and check that f to the n is in fact a vector space. It just helps you become more comfortable with the axioms and how the properties are checked. Okay, so that's the definition of a general vector space over a field. And that's one example of a vector space. We'll look at some more examples later. But this is the canonical example. So we have that f to the n is the vector space over f. So r to the n is in fact the vector space over r. C to the n is a vector space over c. Q to the n is a vector space over q. Q is a field. So you can have q to the n. So that's the most simple example of a vector space. But of course, in order for you to have a useful definition, we want this to be more than just Rn, right? Or f to the n. We want more examples of vector spaces. So we'll take a look at that in another video. Thanks.